Happy morning to all. Up to last class, we discussed Unit 2, the quantum mechanical model of atom. In that video, discussed what about the basic introduction of atom. Then, what are the theories or the laws proposed for the model of the atom. Into the theories, we discussed the main theory is a Bose model of atom. So, based on the Bose model of atom, we discussed what about the de Broglie equation. Then followed by the de Broglie equation, the quantization of angular momentum. So in this session, we are going to discussing about Davisson-Germer experiment, then the Heisenberg uncertainty principle, followed by the quantum mechanical model of the atom by Schrödinger equation. So already we discussed in the last class, if it is electron, it can revolve around the nucleus in a particular orbit. It must possess the quantized angular momentum. That means mvr which is equal to nh by 2 pi. Or else you can say the circumference which is equal to the integral multiples of wavelength. That means 2 pi r which is equal to n lambda. If it is 2 pi r which is equal to m lambda, the electron it can exist in a phase. Or else it can revolve around the nucleus in a particular orbit or particular stationary path. Suppose the 2 pi r not equal to n lambda, that means the electron cannot be exist in space. Sometimes the 2 pi r is less than that of n lambda, the electron will be out of space. Or else 2 pi r is greater than that of n lambda, the electrons are collided with nucleus. So from that we are concluded one thing: if the electron can be revolve around the nucleus, it must possess the definite angular momentum. That means mvr which is equal to nh by 2 pi. Otherwise, the circumference of the orbit is equal to the wavelength of the integral multiples of wavelength. That means 2 pi r which is equal to n lambda. So இது நம்ம என்ன தெரியுதுனாக்கா, டெஃபினட்டா ஒரு எலக்ட்ரான் ஒரு ஆர்பிட்டல் ரிவால்வ் ஆகுனாக்கா it must possess wave in nature. For this concept, we have one experimental proof. That proof is called as Davisson-Germer experiment. The Davisson and Germer is the name of the scientist. In 1927, Davisson and Germer experimentally confirmed the wave nature of electron. They observed by the diffraction of electron beams by crystal lattice. So, இப்போ நம்ம சொன்ன எல்லா கான்செப்ட் இருக்கும் the mvr which is equal to nh by 2 pi. இதுக்கு உண்டான எக்ஸ்பெரிமெண்டல் ப்ரூஃப் யார் கொடுத்தாருனாக்கா Davisson-Germer. ஸோ Davisson-Germer என்ன பண்ணாங்கனாக்கா ஒரு பீம் ஆஃப் எலக்ட்ரானை ஒரு கிறிஸ்டலில் வந்து பம்பார்ட் பண்ணும்போது இட் ஹாஸ் ஸ்கேட்டர்ட் இன் a different direction. அதை பேஸ் பண்ணி they have proved the electron it must possess wave in nature. Now we'll see what about the Davisson-Germer experiment. So in this figure is shown what are the experimental apparatus setup of Davisson-Germer experiment. Here the tungsten filament can be acted as a electron source which connected with high voltage and low voltage power supply. Next, from the tungsten filament the electrons can be allowed to fall on the target molecule will be a nickel. So around the target molecule nickel we have the electron detector and circular scale. ஸோ இங்கே நம்ம என்ன பண்ண போகிறோம்னாக்கா, ஒரு டங்ஸ்டன் ஃபிலமெண்ட் வந்து எலக்ட்ரானை ப்ரொடியூஸ் பண்ணி அதை என்ன பண்ண போகிறோம், ஒரு நிக்கல் மாலிகுல் மேலே நிக்கல் கிறிஸ்டல் மேலே நம்ம வந்து பம்பார்ட் பண்ண போகிறோம். அப்படி பம்பார்ட் பண்ணும்போது ஸ்கேட்டர்ட் ஆகி வர வெளியே எலக்ட்ரான் வந்து டிடெக்ட் பண்ணாக்கா இட் ஆல் பி கேப்சர்னாக்கா ஃபோட்டோகிராஃபர் மாதிரி ஏதாவது கேப்சர் பண்ணணும். அந்த கேப்சர் பண்ண அந்த பேட்டர்னை வச்சு we will prove the electron it possesses wave in nature. Now we will see how the wave nature of electron can be proved by Davisson-Germer. In 1927, Davisson and Germer observed that a beam of electron obtained from a heated tungsten filament is accelerated by using a high positive potential. When this fine beam of electron is allowed to fall on the large single crystal of nickel, the electrons are scattered from the crystal in different direction. ஸோ இங்கே டேவிசன் ஜெர்மர் என்ன பண்ணாங்கனாக்கா ஒரு டங்ஸ்டன் ஃபிலமெண்ட்டை ரொம்ப அதிகமாக ஹீட் பண்ணி அதை அதிகமாக ஆக்சிலேட் பண்ணும்போது அது ஒரு எலக்ட்ரானை ப்ரொடியூஸ் பண்ணுது. அந்த எலக்ட்ரான் என்ன பண்ணுறாங்க, இட் ஹாஸ் அலோட் டு ஃபால் ஆன் த லார்ஜ் சிங்கிள் கிறிஸ்டல் ஆஃப் நிக்கல். அந்த நிக்கல் கிறிஸ்டல் மேலே மோத செய்யும் போது அந்த எலக்ட்ரான்ஸ் எல்லாமே என்ன பண்ணுது, இட் ஹாஸ் ஸ்கேட்டர்ட் இன் ஏ டிஃப்ரெண்ட் டைரக்ஷன். The diffraction pattern so obtained is similar to the diffraction obtained by Bragg's experiment on diffraction of X-ray from a target in the same way. Since X-ray have wave character, therefore the electron must also have wave character associated with them. இப்போ நம்ம பார்த்தோம் இந்த beam of electron ஒரு நிக்கல் கிறிஸ்டல்ல பம்பார்ட் பண்ணும்போது the electrons are scattered at a different direction. அப்படி ஸ்கேட்டர் ஆகிற எலக்ட்ரான் டேரக்டர் பேஸ் யூஸ் பண்ணி என்ன பண்ண போகிறேன், கேப்சர் பண்ண போகிறோம். அப்படி கேப்சர் பண்ணும்போது we get diffraction pattern. இந்த diffraction pattern நம்ம அனலைஸ் பண்ணும்போது it is similar to the diffraction pattern obtained by Bragg's experiment. இங்கே Bragg's experiment ஒன்றுமே இல்லை, ஒரு எக்ஸ்ரே ஒரு கிறிஸ்டலில் நம்ம பம்பார்ட் பண்ணும்போது அந்த கிறிஸ்டலுடைய ஸ்ட்ரக்சர் நம்மளால் அனலைஸ் பண்ண முடியும், நம்மளால் டிட்டர்மின் பண்ண முடியும். அந்த எக்ஸ்பெரிமெண்ட் பேர் தான் வந்து பார்த்தாக்கா Bragg's experiment. ஸோ இங்கே யூஸ் பண்ணுற எக்ஸ்ரே it must possess wave character. Therefore the electron also it must possess wave character. Not only that, நாம் இங்கே யூஸ் பண்ணுற எலக்ட்ரான வேவ் லென்த்து அதே மாதிரி Bragg's experiment யூஸ் பண்ணுற எக்ஸியோட வேவ் லென்த்தும் மோர்லெஸ் சேமாக இருக்கிறதுனால we can conclude that the electron it must possess wave in character. Here the wavelength electron can be determined by de Broglie equation. What the de Broglie equation? Lambda equal to h divided by mv. Arise lambda is equal to h divided by p. So this is the electron diffraction experiment by Davisson and Germer. The beam of electron allowed to fall on the nickel crystal. The electrons are scattered at a different direction. The scattering electron can be captured by a electron detector or photographic plate. So it has to given the diffraction pattern. So this is the diffraction pattern. Circle மாதிரி இருக்கு இல்லையா, இதான் வந்து பார்த்தா diffraction pattern. இந்த diffraction pattern அனலைஸ் பண்ணும்போது it is similar to the diffraction pattern obtained by a Bragg's experiment. So from that we are concluded the X-ray it has wavy nature. Therefore the electron also it has to wavy nature. Not only that, the wavelength of electron and also the wavelength of X-ray also more or less equal. The wavelength of electron can be determined by de Broglie equation. So that's all about the electron diffraction experiment by a Davisson Germer experiment.
MUR is equal to NH by 2 pi. Equation 3. Equation 3 indicates quantization of orbit. Note: if 2 pi r n lambda or 2 pi r n lambda wave is not continually in phase, such an orbit is not possible. This concept gave birth to wave mechanical theory of matter. Limitation: this concept is only applicable to smaller macroparticles, particles like electron, proton. Reason: mass of macroparticles is very small, so wavelength is very large. Experimental proof of this concept: in 1927, Davisson and Germer experimentally confirmed the wave nature of electron. They observed by diffraction of electron beams by crystal lattice.
Davisson and Germer established the wave nature of electrons. Curiously similar setup to the experiment conducted by Davisson and Germer. The setup is placed in an evacuated chamber. It consists of an electron gun G, a nickel target, and an electron detector that is capable of moving on a circular scale. The electron detector is connected to a sensitive galvanometer used to measure current. The electron gun G is used to produce a beam of electrons. The electron gun constitutes a tungsten filament F coated with barium oxide and can be heated with a low voltage power supply. Electrons are emitted by the filament, and these are accelerated at a desired velocity by applying a suitable voltage from a high voltage power supply. The electrons thus emitted are passed through a cylinder with a pinhole along its axis, producing a fine collimated beam. This collimated beam is directed to fall on the surface of the nickel crystal. The electrons are scattered in various directions by the atoms of the crystal. The intensity of the electron beam scattered in a given direction is measured by the electron detector or the movable collector. By moving the detector on the circular scale at different positions, the intensity of the scattered electron beam is measured for different values of angle of scattering. Theta, which is the angle between the incident and the scattered electron beams. This experiment was performed by varying the accelerating voltage from 44 volt to 68 volt. It was noticed that a strong peak appeared in the intensity I of the scattered electrons at an accelerating voltage of 54 volt and at a scattering angle theta equal to 50 degrees. The appearance of the peak in a particular direction is due to the constructive interference of electrons scattered from different layers of the regularly spaced atoms of the crystal. From electron diffraction measurements, the wavelength of matter waves was found to be 0.165 nanometers. We know that the de Broglie wavelength of an electron is denoted by lambda is equal to h by p, where h is Planck's constant and p is the momentum of the electron. If the electron is accelerated from rest through a potential difference of v volt, then, substituting the values of mass of the electron, charge on the electron, and Planck's constant, the expression for wavelength is obtained as 1.227 by square root of v nanometer. In this experiment for diffraction of electrons, the peak value of intensity was observed at 54 volt. On substituting this value in the equation and simplifying, we get the associated wavelength equal to 0.167 nanometer. This theoretical value is in agreement with the experimentally obtained value of de Broglie's wavelength for electrons. The Davisson-Germer experiment thus confirms the wave nature of electrons and the validity of de Broglie relation. The de Broglie hypothesis has been the cornerstone of many advancements and applications in recent times.